been thinking about momentum principle. And, you know, the kinds of things I like to do with the momentum principle don't really completely match with the textbook type problems. But I think that it's important enough to look at some of them and do some examples. And then I will do some examples that would be things like in the textbook, just because it usually approaches it from an F net equals MA approach. And I think I like to talk about the momentum principle. I think it's a little bit better, more useful. So let me just make a couple situations and see if we can work some problems here. So suppose you have a little, we're in space just to make things easier. We don't have to deal with friction, and we're way far away from objects. We don't have to deal with gravity. And I want to do it that way just because it'll be a little bit easier for right now. So let's suppose we're out in space, not in orbit, but just there's nothing around. There's no gravitational forces at all. And I have a little model rocket that's only just 1 kilogram, and it has a little thruster on it. It actually has thrusters on all the sides, so you can fire. You can make it move around. Actually, they do have these kinds of things they want to use in the space station, which has some issues with it. It looks just like there's no gravity, even though there is, and so you can go, psh, 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 and it can move around. Okay. So suppose I have this, say that the thrusters, I'll call it Ft, has a magnitude of, I'm just going to say 2 newtons. Just going to say that. Made it up. Okay. So suppose this is sitting here at rest so that V1 equals 0 x hat plus 0 y hat. And now this little robot fires its rocket. So it has a thrust. So a force this way, Ft. Let's call this the x, y direction. And let's say it does this for 2 seconds. I just completely making up stuff. I didn't want to use all 1s, so I picked a 2. But I used a 2 up there too, so oh well. Okay, so let's find out how fast it's going after 2 seconds. And then we'll find out where it is. And then we'll do something else. So the momentum principle says this. F net is the change in momentum over the change in time. Okay, so I know F net, in this case, is going to be just the thrust, which is going to be, it's pushing that way, so 2 x hat newtons. You really need units. And the change momentum, I know the initial momentum, and I want to find the final momentum. So I can write this as 2 newtons x hat equals the final momentum, mv2 minus mv1, all over the change in time. Remember, change momentum is always final minus initial. That's how we find the change. And there's my net force. I should have left it at Ft, but I didn't. And momentum is mass and velocity. So I want to solve for V2. So let's first multiply by delta T. Let me just write Ft, F thrust. That way I can do it first just as a, without putting any numbers in. So I get Ft times delta T equals mv2 minus m0 vector. Because, and I can do it in this case because the initial velocity was 0, so that's the 0 vector. If I take mv minus the 0 vector, mv2 minus the 0 vector, I still get mv2. So now I can solve for v2. You have to be careful when you're dealing with vector equations. You can multiply vectors by scalars. You can add vectors together. You can divide is the same as multiply. Okay, but I can't divide by a vector. You can't do that. It doesn't follow the same rules. So, but if I divide both sides by m, I get v2 equals ft delta t over m. Now, I can change this to a scalar equation by just looking at the x components. The x component of this should be equal to the x component of that. So I have v2x equals ftx delta t over m. And now I can find out what those things are. I had 2 newtons, 2 seconds over 1 kilogram. And so that's going to be 4 Newton seconds per kilogram, which is 4 meters per second. Because 1 Newton is a kilogram meter per second squared. So multiply by seconds, I get meters per second times kilogram. I divide by kilograms, I get meters per second. So after I fire this thruster for 2 seconds, the rocket robot thing is moving 4 meters per second. The problem would be exactly the same if it was already moving at 2 meters per second. I would have found the change in velocity is 4 meters per second, so it'd actually be moving 6 meters per second. Okay, now, if it started at x equals 0, it started at the origin, can I find out where it is after that time? Now here, I can use the following idea. I can say v average in the x direction, we only have x direction here, is delta x over delta t. That's true if my velocity is changing at a constant rate, meaning I have constant forces, then that's true. Or if the velocity is constant. Or if I can approximate it if the time interval is really small. So it is true here. I can use that. So the average velocity in this case is just going to be 4 meters per second plus 0 meters per second over 2. 2 meters per second. And then I have x final, x2 minus x1 over delta t. So that's 0. So x2, you probably can't see that. I'm not sure where my camera is. I'm going to erase this. So I get x2 is equal to 2 meters per second times delta t of 2 seconds. So it's going to be 4 meters. So it started at x equals 0 and it ends up at 4 meters. Maybe this is a bad idea because it ends up at 4 meters and its final velocity is 4 meters per second. But those aren't necessarily related. So, oh, I got a phone call. Okay, so let me stop there.